This talk will describe how deep optics can be used to design a single-shot high-dynamic range imaging system. High-dynamic range imaging is important for many computer vision and graphics applications, such as photography, image-based lighting, high-dynamic range display, scientific imaging, autonomous driving, and manufacturing. While natural scenes often exhibit a high dynamic range, this range is difficult to accurately record with a conventional image sensor. Any exposure setting results in either underexposed dim areas or overexposed bright areas. By adjusting the exposure, one can control which portions of the scene are properly exposed. Several popular high dynamic range imaging techniques exist. For example, one can capture several photographs with different exposure settings, use camera systems with multiple sensors, or use an array of neutral density filters or custom sensor circuits to create spatially varying pixel exposures. However, sequentially captured images can create ghosting artifacts. Multi-sensor systems are costly and difficult to calibrate, and spatially varying pixel exposures require custom sensors or sensor circuits. Recently, neural network-based in-painting methods have been proposed that estimate the details in the saturated regions of a scene. Unfortunately, these methods can only hallucinate the missing details. A promising idea to optically encode bright scene details into a low dynamic range image was proposed by Roof et al. They used a photographic filter that creates a star-shaped point spread function. This PSF spreads otherwise saturated details into the other parts of an image, which are then recovered via deconvolution. Although interesting, this optical filter design was heuristically chosen and is not optimal. In this work, we introduced the end-to-end design of optics and image processing for single-shot high dynamic range imaging. In a training phase, we learn an optical filter whose point spread function encodes high dynamic range information into a single low dynamic range exposure. Using a CNN-based reconstruction technique, our method then allows the high dynamic range image to be recovered. The first step in designing an optical filter with end-to-end learning is to model the optical system. We do so as follows. We first model a high dynamic range scene that is located infinitely far away from our sensor. Light from the scene propagates to a custom optical filter located at the aperture plane of our camera. This is what we're going to optimize. Light is modulated by the filter and then immediately interacts with a simple lens, also located at the aperture plane. This modulated light then propagates to the sensor, which records a clipped and noisy version of its intensity. We compute the point spread function associated with the system by propagating a plane wave through it. With this optical model in hand, we did the following. We composed a training dataset consisting of thousands of high dynamic range images. For a given optical filter, we simulate the corresponding point spread function, as described in the previous slide. This PSF is used to simulate low dynamic range sensor images in a physically realistic manner by convolving the high dynamic range input image, saturating them on the sensor, and then adding noise. A CNN then processes the sensor images to estimate the high dynamic range scenes. Using some loss function, we calculate an error, which is then back propagated not only into the parameters of the neural network, but also all the way into the physical design parameters of the camera, here the surface profile of the optical filter. The optimized optical filter resembles a grating, which creates a PSF with several peaks. Such a PSF creates multiple differently scaled copies overlaid in the same sensor image. The entire system works together as follows. A simulated captured low dynamic range measurement looks like this, with a close-up of the brightest region shown in the bottom left. Note the copies of the fireworks. The network takes this low dynamic range image with copies and uses the copies to fill in the details of the saturated region. See the 3 circled flares in the reconstruction. Without a PSF, a similar network can only hallucinate plausible details, which may look nothing like the ground truth. Here, the network's reconstruction is missing a flare. Using extensive simulations, we show that our end-to-end approach outperforms the CNN-only approach and previous heuristic filters using a variety of different error metrics, such as peak signal-to-noise ratio in the linear and gamma-corrected domains, and also perceptual error metrics, such as HDR VDP2. We fabricate the optimized lens using grayscale lithography and mount it as an add-on on a conventional camera lens. The simulated and captured PSFs are very similar. We captured several high-contrast scenes with our prototype. The PSF of our system is used to create copies of the bright, saturated details, which are then recovered with the network. In contrast, the CNN-only approach is forced to fill in missing regions with blob-like structures. It doesn't know anything about the overexposed areas, and so can only hallucinate a plausible guess. Here's another example scene that was captured outdoors at night. Thank you for listening. For more information about this project, including code and datasets, please visit our website.